So students, and Diwali is over, right? And it's almost 1 year now. Last year at this time only we started our classes, 15th of November if I remember correctly. And today is 14th of November. 1 year is over. Okay. So in 1 year, almost have finished the syllabus. Right? Few things are there. And may take 15 more days and we will finish everything. So today what then? Live class. So 12th syllabus first. So today, P-type semiconductor. In the last class, we were doing N-type semiconductor. We discussed it. What is N-type? Now today, we will discuss P-type semiconductor. Okay. So what it is? P-type semiconductor. P-type semiconductor. What it is? It is impure. We know that. Okay. Pure were silicon and germanium. And we saw that if we are taking pure semiconductors, we are not getting enough charge carriers so that enough current we can make flow through that. Okay. So that's why we did doping. Right. So doping means what we were doping? Pentavalent impurity we doped when we were talking about N-type semiconductor. So what that pentavalent impurity gave to us? Extra electron. Okay, one extra electron from an atom which we were adding. Right, and how much we were adding? I told you that we normally have the concentration, we measure in ppm, parts per million. That means one atom in 10 to the power 6 atoms of the pure semiconductor we add. Right? Okay, so here also we are going to add an impurity. A p-type semiconductor means we are going to add a trivalent impurity. Silicon is having how much valency? 4. So we are adding trivalent impurity in that one. Okay, trivalent impurity. Trivalent impurity is added to make semiconductor or silicon or germanium as p-type semiconductor. As p-type. Right. N-type semiconductor, what happened? It gave an excess electron. So we call it as donor impurity. This is having 3 electrons on it. So 3 electrons are going to be shared with silicon. But then one will be remaining, right? If suppose we put trivalent impurity means the which element we are going to put which is trivalent, okay, and which is near to silicon or germanium maybe. Okay, that is what we have to see. So what the examples are first of all? Examples are aluminum is there, I think, boron is there, many will be there, but aluminum and boron are there. Okay, so this suppose aluminum we are choosing. So aluminum is having 3 electrons, right? So aluminum we have taken over here. So 3 electrons are here in this. One will take over here, one will take over here, one will take over here. And it is surrounded by what? Silicon. Okay. All the sides it is surrounded by silicon. So here is silicon, here is silicon, here is silicon, here is silicon. Okay. Silicon's electrons are also there. This is silicon's electron. Silicon has how many? 4. Okay. These are 4. This is here also. And here also. Now what? They will be shared. Okay. This is shared here. This is shared. This is shared. But here there is a vacancy. Okay. There is nothing to be shared. So there is a vacancy now. Okay. So to complete covalent bond, what will happen? Electrons from other places will come. Other places means other atoms will come and jump over here. When slightly energy is given. At 0 Kelvin if we talk, this is how it is. Okay, there will be vacancy in that. And this vacancy only we are calling as what? Hole. As the temperature goes up, because normally we will be using at room temperature 27 degrees centigrade. At 27 degrees centigrade, electrons will get energy and they will jump. When the electrons are going to jump in that one, what will happen? This hole will move in place of those electrons from where the electrons have jumped into this one. So we will say that hole is moving. Actual motion is for electron, but here we will say hole is moving. Okay. So this way, once we are getting the motion of electron, we will be saying that yes, current is there. Okay. And since we are going to use it at room temperature, so we know that certain amount of bonds will break. Okay, certain amounts of bonds are going to break. That means we are going to get electrons also. That will be in conduction band. Okay, and majority will be here because holes are created. One atom which is being added into this one is creating one hole. So mainly there will be holes and less number of electrons will be there. Okay, so who are the majority charge carrier in this p type? Holes. Okay, majority charge carriers. Majority charge carriers are holes. Majority charge carriers are holes. And minority charge carriers are electrons. From where electrons came? Electrons are in conduction band. Okay, from where they came? Because certain covalent bonds are broken. Okay, and electrons get energy and those electrons will go to conduction band. Okay, so minority charge carriers are electrons. Okay, first you note this one, then you make the band diagram. There I will explain you more. Okay, first you do note this one first. Any doubt is there, students? Please ask. Completed. Okay. So this aluminum or boron, this trivalent impurity is called acceptor. Okay. In N-type semiconductor, what we saw? We saw that this impurity that you are adding, it is giving an extra electron. We call it as donor atom. This is acceptor atom. Okay. So this is actually acceptor atom. Who? The trivalent impurity. Okay. So now let's make it into the band diagram. How it is, where it is. Okay. So band diagram is like this. So if here is valence band, BB, Okay, so when we are mixing trivalent impurity, okay, so what these electrons are doing, which are available, they are making covalent bonds. And then there is hole created. Hole is also in which, where? Very close to valence band. Okay, so acceptor atoms, okay, holes, whichever holes we are saying, are very close to what? Valence band only. So here only we can make those holes. Like here. Okay, these are holes. Right? Energy gap is very less. Because we said no. Which electrons are going to jump and fill the vacancy? When you are giving energy to electron. Because all the electrons are where? They are already engaged in their own covalent bonds. In pure semiconductor also will be had silicon or germanium. All the electrons were engaged in covalent bonds with their other own atoms. Okay. So here also they are all engaged. If you have added trivalent impurity, fine. The trivalent impurity is also making covalent bond, but there is a vacancy. Who is going to fill it? Obviously the silicon. Silicon electron is going to come and fill it, right? So then how it will be getting free? When you are giving it energy. A slight energy is required to come and fill these bonds. So they are close to valence band. Okay. This is acceptor atom. Okay. These are holes. Okay. And here somewhere is conduction band. This is conduction band. Now in this one we can show certain electrons also, because we know that the covalent bonds are going to break. So when they are breaking, electrons, certain electrons will go up. Okay. The electrons also will be there. Certain electrons we can show. These are electrons. And here what will show in valence band? Both. Majority will be holes will show. In this one holes will show, and that's all. Okay. Clear? So in valence band we are showing you holes, 1 or 2 electrons if you want to show, that also is fine. Conduction band electrons. Okay, and here energy gap also you can show around 0.05 eV. Right, note that one. This is P-type semiconductors energy band diagram. Then completed, students? Alright. Right, let's talk about conductivity. Conductivity in semiconductors. We all know that conductivity is because of holes also and electrons also. Both are available. One is majority charge carrier, one is minority charge carrier. In P-type semiconductor, what was there? The number of electrons were way less than number of holes. Okay. So NH greater than number of electrons. Whereas in N-type semiconductor, number of electrons were greater than number of holes. Okay. Right. So conduction in semiconductors. So we all know the total current is because of current to electrons as well as current due to holes. Where are holes moving? Valence band. Where are electrons moving? Conduction band. Okay, so this will get in conduction band and this will get in valence band. Right, but what we want basically here? We want conductivity. Okay. So conductivity, what relation we had? If you remember current, electricity, we had one relation which was E equal to rho J. Rho is resistivity. Okay, so if you want to have this in conductivity, we can write this as E equal to 1 by sigma into J. Right, this is in conductivity terms. So J equal to sigma E. Fine. J we can write as I by A. J is current density. Okay, so this is I by A equal to sigma I. And I is what? Recollect current, electricity only. NEA VD. VD is what? Drift speed. Okay. NEA VD by A equal to sigma I. Fine. A and A cancel. Then what? Then NE VD by E equal to sigma. Drift velocity per unit electric field. This is called mobility. Mobility of charge, mobility of electron, mobility of holes. Okay. So sigma value that we are getting is Ne mu. What is mu? Mobility. Okay. Mu is mobility. Okay. Mobility of charge carrier per unit electric field. Mobility of charge carrier per unit electric field. Okay, but we have here holes also and electrons also. So sigma for electrons, it will be number of electrons, charge on electron into mobility of electron. Sigma for electron, same way sigma for holes. Okay, number of holes into E to mu H. Charge is same because we know that holes are moving, actually who is moving? Electron is moving. Then why mobility is different? Mobility is different because it's moving in valence band. Its speed will not be, drift speed will not be same as it is in conduction band because it's free in conduction band. This mobility is a lot more as compared to the mobility of holes. Okay, so these are conductivity of electron and holes in conduction and valence band. Okay, note this first. Any doubt is there? Ask me. Completed? Okay. So total conductivity will be what? This plus this. Okay. Total conductivity, if we are talking, it will be sigma equal to sigma E plus sigma H. And what is sigma? Say N E E mu E plus NH E mu H. Okay. This is total conductivity. Okay. Now in semiconductor, what happens? Semiconductors, if you are increasing the temperature from 0 Kelvin, as you are increasing the temperature, what is happening to conductivity? It's increasing or decreasing? Answer is increasing. How? Because charge carriers are increasing, bonds are breaking. You are getting electrons in conduction band, you are getting holes in valence band. So conductivity actually increases as you increase the temperature. But when you talk about a conductor on increasing the temperature, what increases? The resistivity increases. Resistivity increases means conductivity decreases. Okay? In semiconductor, conductivity increases on increasing the temperature. On increasing the temperature. Okay, whereas in conductors, conductivity decreases on increasing the temperature. Okay, remember that this question is asked many times. Right? Note that. Done? Completed, students? Okay. Let's do a simple problem now. A simple problem says the energy gap between valence band and the impurity that we added, P type. Okay, valence band and the energy of the holes. Okay, the energy gap between valence band and P type acceptor atom energy is 50 milli electron volt. Okay, find minimum wavelength of light required to excite electron to jump to holes in acceptor atom. Okay. So it's not conventional question of semiconductor. It's a different question. Okay, they are mixed up. Two topics. Okay. So note this one and find its answer. If you remember how to solve it, solve it. Yes, students. How to do you? This is the minimum energy required. How much is it? This is energy is 50 milli means 10 to the power minus 3 electron volt. Okay, that means 5 into 10 to the power minus 2 electron volt. And we all know that when electron volt is there and we have to find wavelength, what we used to do. Okay, so lambda is 12,400 by what? Energy in electron volt. Energy in electron volt. 5 into 10 to the power minus 2. Okay, so what's going to come? 12,400 into 100 by 5. This is 20. What we are getting here? 8, 4 and 2. Okay, 8, 4 and 2. Then 3 zeros. Okay, note that one. To 48,000 angstrom. Done? Completed, students? Okay. Right. Now then, let's do a few questions on mixing also. Okay. So what question is there? Suppose we have germanium. Okay. Germanium, we have germanium sample. Okay, and you say the concentration Ni. Okay, Ni is 10 to the power 19 per cubic meter. Okay, now in this one we are mixing aluminium. Aluminium means trivalent. Okay, aluminium is mixed. Okay, and whole concentration become 10 to the power 21 per cubic meter. Question asks you, what is the concentration of electron? What is the concentration of electrons? Come on, that answer you give me fast. We have done this similar question in during N-type semiconductors, I guess. Okay, come on, do that fast. Give me the answer. Yes, students, what is the answer? Hmm? Number of holes are given 10 to the power 21. And what is the formula we have? Ni square equal to Ne into Nh. So Ni is how much? 10 to the power 19. So 10 to the power 19 square. Ne we are finding, and this is 10 to the power 21. This will be what, 34. Okay, 34. This is what, 19. Okay, this is 10 to the power 38. 10 to the power 38 by 10 to the power 21. 10 to the power 17. This will be 10 to the power 17 per cubic meter. Simple question. Okay, note it. Note it fast. Done? Yes. Okay. Now one thing you tell me. When we are adding the impurity, what is happening to energy gap? Is energy gap increasing or energy gap decreasing? What is energy gap actually? Energy gap is the energy you require to send the charge carriers for conduction. Okay, so that we can get current. Normally in pure semiconductor, all were engaged. They were covalent bond with all. Then you have to break that covalent bond, send some electron to conduction band, okay, so that we can get the conductivity, we can conduct the current. Right, now you have added impurity. With impurity, what has happened? The energy gap has decreased or energy gap has increased? Answer is energy gap has decreased. We have to give less amount of energy to make conduction happen. Let's talk about p-type semiconductors. In p-type semiconductors, what is there? We saw that energy gap 0.05 eV. Okay, between where the holes are and where the valence band is. So just we have to make electron to move to the that vacant holes in p-type semiconductor, right? If that's going, and immediately we are getting the current, right? So energy gap decrease. Exactly same way if we talk about n-type semiconductors. N-type semiconductor also, where are those free electrons? Those free electrons are very close to conduction band. So very less amount of energy is required to send them to conduction band. Okay. So with impurity, energy gap, energy that is required to make those charge carriers available for conduction is less as compared to pure semiconductor. So what we will be adding, an important point is, remember that on doping, energy gap decreases. Okay, on doping, energy gap decreases. Note that one, important point that is. Then we solve another numerical. Okay, then see. Now suppose that we have one pure semiconductor which is silicon. Okay, silicon is there. And for silicon it is given that it is having 5 into 10 to the power 28 atoms per cubic meter. Okay, silicon is having 5 into 10 to the power 28 atoms per cubic meter. And in this one pentavalent impurity we are adding. Okay, pentavalent impurity is added in ppm. That means 1 atom per 10 to the power 6 atoms of silicon, we are adding one pentavalent impurity. Okay, right. Alright. Then how much was Ni, the concentration of charge carriers in silicon? Okay. Ni value, let's say is 1.5 into 10 to the power 18. Okay, per cubic meter. It was there, Ni for silicon. Okay, this was Ni value. So, what do you want now? Find number of holes here. Find number of holes in which type of semiconductor will be this N type, like number of holes in or concentration of holes in N type semiconductor. Not number of holes, concentration. Okay. Find concentration of holes. Okay. Find concentration of holes in N type semiconductor. Okay. Note the information. Then see then what it is. Pentavalent impurity means what? It's a donor impurity. Okay. So how many electrons we are adding? That is the first thing. This is donor. So electron it will add. How many? It says ppm. 1 in 10 to the power 6 atoms of silicon we are adding this pentavalent impurity. So how many are there? 5 into 10 to the power 28. So how many we added? 5 into 10 to the power 28 by 10 to the power 6. So these many free electrons we are going to get. Okay. So concentration of donor electrons. Donor electrons is 5 into 10 to the power 28 by 10 to the power 6. That is 5 into 10 to the power 22 per cubic meter. This number of electrons. How many number of holes are there? This. In pure semiconductor, these many holes for the 1.5 into 10 to the power 18. Okay. And how many electrons are there now? 5 into 10 to the power 22. Now this is a lot more than, okay, a lot more than this. Right or not? So these will be the number of electrons. He is asking number of holes. How many number of holes are there? So what he will do? We know that Ni square equal to Ne into Nh. These are number of electrons now, remember. Okay. You don't have to add whatever earlier were available because this is very less as compared to this. So directly we can use these are the number of electrons. Okay. So Ni square is square of this. So 1.5 into 10 to the power 18 square. The number of electrons, this 5 into 10 to the power 22 into number of holes. How much we are getting? 1.5 square means 2.25. 2.25 into 10 to the power 36 by 5 into 10 to the power 22. Okay, so this is 4.5 here, now 0.45. Yeah, 0.45 and this is 10 to the power 14. So 4.5 into 10 to the power 13 per meter cube is number of holes now. Okay, so these are the number of holes. This way we calculate. Whenever it is given that how much is added in terms of ppm, get the value of, suppose if it is trivalent, then this would have been the number of holes. This would have been number of holes. Okay, so this is the way. Note that one. Any doubt is there? Ask me. Any doubt, students? All right, note it. Done. Completed, students? Okay. Let's do one question on conductivity also. The question says you that, let's say in a semiconductor, Ni is 1.5 into 10 to the power 12 per centimeter cubic. Okay, then mobility for electron. Mobility of electron, let's say, is how much? 0.5 unit. Now, and mobility of holes, we will say, is 0.1. Okay. Question says find conductivity of given sample. Conductivity of given sample. Alright, I have given you the value. Let's note this one. Units. Find the conductivity of the sample. What we have to do? Add both. Sigma equal to what? Sigma due to electron plus sigma due to holes. What else? Sigma due to electrons is what? Number of electrons into mu E plus number of holes into E into mu H. Now it's a pure semiconductor. We have given Ni is given this. So that means number of holes are also same and number of electrons also same. Okay. So Ne equal to Nh given to you. Both are equal to Ni. Okay, so we can take it outside. Ni is outside, E is also outside. Now remaining is what? Mu E plus mu H. That's it. Mu E plus mu H is 0.6. So Ni is 1.5 into 10 to the power 12. This is 1.6 into 10 to the power minus 19. And this is 0.6. Okay, so this is 10 to the power minus 7. This is 1.5 into 0.6 means 0.9. 0.9 into 1.6 into 10 to the power minus 7. 1.6 into 0.9 is how much? I think 1.44. 1.44 into 10 to the power minus 7. Okay, it's a conductivity. So conductivity's unit is mho per centimeter, is it? What is resistivity's unit? What it is? Ohm centimeter. Resistivity's unit, right? Ra by L. Ohm centimeter square by centimeter. So ohm centimeter. So inverse. Inverse means what? Ohm inverse means mho. Okay, so mho per centimeter. Okay, that's the unit of conductivity. Note that one. Completed, students? Students completed? Okay. Now we are going to see PN junction. That means P and N we are going to fuse together. We call them as what? Diode. So PN junction only we use. Separately P-type semiconductor or N-type semiconductor are not that much useful. Okay. P and N when we are combining, then only we are getting the desired results. Okay, and we are getting different kind of characteristics of them that we are going to study. And this is called what? Diode. This is called diode. That means one will be anode and another will be cathode, and then there will be flow of current between them. That is what we are going to see. So one P-type semiconductor, N-type semiconductor we are fusing. Okay. Fusion of P and N type of semiconductor. So what's happening in this? Let's see. First of all, P-type semiconductor crystal we are taking. So how it is? Now when P we are saying, that means it's already mixture of maybe silicon if you are taking. Okay, and one trivalent impurity. Right? So P, we are showing P over here. P-type semiconductor. Now P-type semiconductor means it is having what? It is having maximum holes. Okay, and few electrons will be there. Few electrons will be where? In conduction band, and maximum will be holes in valence band. So how to show that? Maybe we'll show it like this. Okay, these are all holes in this. This is P-type, and few electrons you can show here and there. Okay, this is P-type. Same way we will show N-type over here. N-type, how will we show? This is N-type semiconductor. N-type semiconductor means there will be maximum electrons will be here. Okay, and there will be some holes we will show. Something like this. Right, this is N-type. Now we are fusing them. Fusing them means we are bringing it close. Okay, suppose we are bringing it like this. They are fused. Now what is going to happen? Now we know that when we are talking about N-type semiconductor, where are those electrons? Conduction band. Okay, and these are the electrons which have high energy. Right. So what will they see? They will see this valence band over here. These vacancies they will see. Okay, in P-type. So what will happen? They will jump. So these electrons will come here. Okay, the electrons will jump. means high kinetic energy, electrons are going to jump, right? Then what is going to happen? When we talk about N-type semiconductor, we talk about P-type semiconductor. Actually, they are neutral. How they are? They are neutral. Okay. When you mixed up, suppose silicon with boron, when we are mixing, silicon was neutral in itself, boron was neutral in itself. When you mixed up, anything has gone out? No. Everything is inside. So, this is actually a neutral crystal, and this is also a neutral crystal. Now, what has happened? Electron from N jumped to P-type. So, what will happen? This became negative and this became positive. Okay, electrons have jumped. Why they have jumped? Because these were energetic electrons. They had the energy. So, they jumped to occupy the vacancy which was there in P. So, they jumped. Okay, so what happened? They jumped. This here became positive because they lost the electrons, and this become negative because they got the electrons, right? So, what will happen next? Next is one more diagram like this. Okay, we'll make it one more diagram like this. If you are going to make, say here, okay, slightly smaller we can make it. Not this entire thing we want to select. Possible? Okay. Oh, they selected entire. Okay, fine, no issues. So what do you do? This is what we got now. Then this has moved here. Electron has come over here now. This is electron. Okay, this is electron, and this is hole. Right. This is hole here. And we are saying that what has happened? It has lost the electron. So this has become positive. And this has got the electron. This has become negative. Okay. So one layer they make over here. This is the layer. What layer? Because this is positive here. This is negative here. So electric field is there. Inside this. And this we are calling as depletion layer. Okay. This happens immediately. Immediately this happens. Very fast. As you fuse, it will be happening. Now what will happen? That this electric field is there. When this electron wants to jump over here, it doesn't allow. Why? Because electron always move opposite to electric field. So this electric field is going to apply force on this electron in this direction. So it's not allowing these electrons to move to this direction. Okay. And it's not allowing these holes also to move in this direction because holes will move in the direction of electron because these are positives, right? They move as if a positive charge is moving. Who? Holes. So these are not able to go there. These are not able to go there. So these electrons now are not able to diffuse because of this electric field. Correct? Clear? So what is the first step? High kinetic energy or high energy electrons move towards holes of P-type semiconductor. P-type semiconductor and occupy the vacancy, right? There is no problem in that. Occupy the vacancy. Now, because of this, when electrons have moved from here to here, definitely current we will be getting. So, this current, because of the motion of these electrons, is called diffusion current. Okay, we got diffusion current. Correct. So high energy electrons move towards holes of p-type semiconductor and occupy the vacancy. The current obtained, the current obtained is called diffusion current. Okay, then what happened? As I told you, that electric field is set up. Why? Because n-type semiconductor has lost the electron and p-type semiconductor has got the electron. Okay, so due to diffusion, of electrons at junction, this is junction, okay, this is a junction. At junction, one small layer is created. What we are calling it as depletion layer, which prevents further diffusion of electrons. Further diffusion of electrons. Okay, why it does so? Because there is an electric field, and this electric field is applying force on these electrons in opposite direction and this holes in this direction. So further diffusion is not possible. Okay, but let's discuss about the other charges. Holes cannot move this side, electrons cannot come this side. But what about these electrons? These are also conduction electrons. These. Okay, when these conduction electrons try to pass this side, they are able to pass. They are able to go. Whatever vacancies are here in this one, they are able to occupy. Why? Because this electron, when this goes clear to this one, electric field is in this direction, so this electron definitely can pass. Okay, this electron definitely can pass through this. So this here is called drift current. What current is this? This is drift current. When minority charge carriers are able to pass through this depletion layer. Okay, this is called drift current. There was diffusion. This is drift. Okay, first you note this all, what I have written, then I will tell you more about that. Come on. Then clear students? Okay. So you're talking about drift current. What is drift current then? Drift current when minority charge carriers from P. What are minority charge carriers? Electrons. So when minority charge carriers from P-type semiconductors move to N-type with the assistance of electric field, obviously. Okay, with the assistance of electric field. Drift current is obtained. One more way is there in which drift current is obtained, that is, if suppose in depletion layer, within depletion layer. Now, depletion layer means is something like this. This is here positive and this is negative. Okay. Positive means holes. Okay. Here holes are there and here electron is here. Electric field is like this. This is N type here and this is P type. Now, suppose that here some covalent bonds are broken within depletion because this is the region. Okay. This is the region. So, in this region, if suppose any covalent bonds are broken, suppose there is electron. Covalent bonds are broken. Okay, there is a covalent bond. The covalent bond is broken, that means this electron also has to move. Where it will go? Because of this electric field now, electrons will go where? This side. So this also is contributing drift current. This is also drift current. Okay. How was diffusion current? Like this. This was diffusion current. And how is drift current? Like this. Am I correct though? Or have I written it in the wrong way? This is direction of electron. Sorry. This is diffusion current. Because current will always be in the opposite direction of the electron, right? I wrote direction of electron only. And how is drift current? Opposite to this. This is drift. Let me check in the previous slide also. Previous slide what I have done. Where is drift current? Okay, I have not shown the direction. Diffusion is okay. Okay, so diffusion current is this, drift current is this. These are also causing drift current. What is that? Breaking of covalent bond in depletion region. Okay. So drift current, right? At normal temperature, drift current and diffusion current used to be of the same magnitude. That means how many electrons, because of excess energy, are able to pass over here. More or less, same electron will be going back in the form of drift. So, total current that we get at normal temperature is 0. We are not getting any current. Okay, neither diffusion is there nor drift current, significant values there. Both are adding and becoming 0. Okay. So, at normal temperature, current obtained in PN junction is 0. Right? Note that. Completed. Okay. Now, this depletion region, this depletion layer that we have studied here, this very small, as I said, its width is nearly equal to 10 to the power minus 6 meter. Okay, and since electric field is there, depletion region's width also is there. If I say that, okay, 10 to the power minus 6, but if I represent this as D, then there is potential difference also. Okay, there is potential difference also. And how much is this potential difference? We said it's delta V. And this delta V will be called what? E into D. So electric field into D. That is delta V. And this delta V, the potential difference, called as barrier potential. This is called barrier potential. Okay, this is called barrier potential. There is a potential difference between these two ends of depletion layer. Okay, note that one also. 10 to the power minus 6 meter approximately is the width of this one, and potential difference is delta V equal to ED. Done. So sometimes they show in with the diagram also, like suppose PN junction diode they have made an electrical circuit. Okay, this is a PN junction diode. This is a depletion layer, and then it is like this. Okay, so just to show the potential difference over here, they'll make it like this. Okay, this is potential difference graph. Correct on yeah. Okay, so this is delta V, and this is T. Let me show you like this. Okay, even I have made it wrong. Wait. Let me make it slightly bigger. This is your PN junction. This is depletion layer. Okay, this is T. Okay, now we can show it. Okay, this is VD, this is barrier potential. Taking this as 0, okay, and this is P value. Or sometimes they'll show you the negative also. Okay, like this also, like this is negative here and this is positive. I have shown you this negative means 0. So from 0, it is going up. Okay, this is increasing, it becomes positive, and this is the potential difference. Right? Note that one. Or you can make a graph also. The graph when you are showing, take it from negative only, like this. Okay. Like this. Okay. So this way you can show in the diagrammatic way. Done? Okay, students, done that? Okay, so today we are finishing here, students. The next class we will see its properties and its applications. So maybe Thursday and one more class. Saturday it will be over, and by that time your thermodynamics also will be over. Okay, so after thermodynamics, what do you want? Problems on thermodynamics. Yes, that will be in live class, but a recording of which chapter after thermodynamics? Okay, Ashini? Okay, so we will start waves after that. You don't want kinetic theory of gases or thermal properties? Hmm? That's what I am saying. That's why I am asking. No, so after this, we can go for KTG also. Kinetic theory of gases. Yes, Ashini, shall we do that, or shall we go to waves? Okay, KTG shall we do? After this KTG, maybe 3 classes. It's a small topic. 3 classes, 3 or 3 recordings will be there for that also. So we'll finish that one, then we'll move on to waves. Okay? All right then. Okay, students, see you in the next class. Bye bye.